Log on, tune in, find out. Another good idea from Cambridge.
Who is the Jean Beer Distinguished Professor at Washington University in St. Louis. Lihong has written one of the first textbooks in the field, Biomedical Optics Principles and Imaging, which has won the Joseph Goodman Award. He has an incredible number of breakthrough inventions, published over 250 journal articles. He is the editor-in-chief of the Journal of Biomedical Optics. And more recently, he was awarded the C.E.K. Nice Medal by the Optical Society of America. And the motto for this award is that optics transcends all boundaries. So maybe you'll forgive me if, for the purpose of this afternoon, we'll modify that to mathematics transcends all boundaries. And if you've never seen Lihong's images, you're really in for a treat.
Thank you, Adrian, for the very kind introduction. So I'll be talking about photoacoustic tomography. Our goal can be summarized in one phrase. We want to ultrasonically break through the optical diffusion limit. My university requires me to disclose my financial interest in two companies for every talk I give. Microphotoacoustics and Endra both are commercializing photoacoustic tomography. We're funded by NIH. Starting from the motivation challenges in this field, I'll cover two main areas of photoacoustic tomography, namely photoacoustic CT and photoacoustic microscopy. Now close with a discussion and summary. Why optics? We have so many imaging modalities already. First of all, it's very safe to use light because we're talking about photon energies of a couple of EVs instead of thousands of EVs used in X-ray or PET. So optical photons are non-carcinogenic. From the physics perspective, which is a very fundamental level, in the entire EM spectrum, there's a tiny region for optics. And that's the only region that allows you to probe molecules directly. So we have molecular imaging to begin with. From optics, we can talk about all sorts of contrast mechanisms, absorption, scattering, fluorescence, and whatnot. But today I'll focus on absorption because the photoacoustics is sensitive to absorption. Optic absorption probes all sorts of biomolecules. Oxyhemoglobin, deoxyhemoglobin, melanin, lipid, even water, which is transparent in the visible spectral range, but becomes absorbing in the near-infrared range. Recently, we demonstrated DNA and RNA absorption as well. The list actually goes on and on. Basically, any molecules are absorbing. Physiologically speaking, if you use endogenous contrast, the contrast that's in the body already, we can provide you functional imaging. Basically, we're quantifying physiological parameters such as the concentration of hemoglobin, oxygen saturation of hemoglobin, cell nuclei, or even blood flow by using Doppler effect. Biologically speaking, if we use exogenous contrast, we have to introduce contrast agents to the body. We can provide you what's called molecular imaging of biomarkers or even reporter genes. Again, the list goes on and on. There are many, many reasons why optics is important. Where's the challenge? We face two very fundamental challenges. Diffraction as a wave phenomenon limits the spatial resolution of all ballistic imaging modalities you've heard of. Planar, confocal, two-photon microscopy, or OCT. It has been overcome for super resolution imaging recently. Diffusion, on the other hand, as a scattering phenomenon, limits the penetration of all ballistic imaging modalities. to about 1 millimeter in the skin. We use photoacoustic tomography to overcome this limitation for super depth imaging. This movie shows you how photons propagate in biological tissue. The photon propagation transitions from the early ballistic regime into the later diffusive regime within a matter of 1 millimeter or so. This transition depth is the diffusion limit, which is defined by the transfer mean-free path. That's the transfer mean-free path between equivalent isotropic scattering events. There are two very important decay constants. These are 1/E decay constants. If you depend on ballistic photons, the decay constant is about 100 microns. If you depend on diffuse photons, multiple scattered photons, the decay constant is much longer. It's up to about 10 millimeters. Again, this is a 1/E decay constant. You can go through multiple decay constants, still get sufficient signals. The rule of thumb is roughly up to 10 times the decay constant. So today I'll focus on the diffusion problem. How do you get a good image? Because scattering is so strong in biological tissue, in fact, the mean-free path between the scattering events is the width of your hair, about 100 microns. In such high scattering medium, photons will diffuse very quickly. If you try to mimic X-ray projection, your excitation photon path and detection photon path will be tortuous. The middle plane structure will not give you a shadow directly, extremely different from X-ray projection, because you will work in a single scattering or unscattered regime. So this will not really work so well for high-resolution imaging. But you can still penetrate tissue with diffuse photons up to a few centimeters. Imagine if you slice open the tissue to expose the middle plane. Now your detection photon path is well defined. That will give you a very good image. Even though your illumination photon path remains tortuous, we only need one-sided clarity to get a good image. It could be either the excitation side or the detection side. Today I'll focus on the detection side by using photoacoustics. Well, that's not very useful for imaging because it's invasive. A better idea is to keep the tissue intact, but use osmotic agents to optically clear the tissue. And that allows you to form a very good image as well, but optical clearing is toxic. So still not quite so useful for in vivo imaging. A much better idea is to convert light into sound through the photoacoustic effect. Acoustic scattering is 1,000 times weaker than optical scattering. As a result, we achieve the equivalent to case B or case C without invasiveness or toxicity. We're essentially listening to optical structure because the contrast comes from optical energy deposition. We're revealing optical contrast by detecting sound. So it's a hybrid modality. The phenomenon of photoacoustics was first reported by Alexander Graham Bell over 100 years ago. He had this notion of photophone instead of telephone. The idea was to encode sound into a light beam, then propagate the light beam in space, then convert light back into sound again for communication. This idea never really took off because the propagation requires line of sight, which is hard to achieve in many cases. What we're interested in is this spot, which has the photoacoustic effect. So light is first absorbed, which generates a temperature rise. Due to thermoelastic expansion, we generate acoustic emission. Well, Bell was interested in audible frequency range. We are interested in the ultrasound frequency range. Over 100 years ago, of course, tomography was not even in the lexicon. Today, we're applying this very old physics to a modern concept of imaging. You can start with the wave equation, but without jumping into that wave equation, we can show you the bottom line. Typically, we use a nanosecond laser pulse, which is short enough to consider that as a delta pulse. At the end of the delta pulse excitation, you get this initial pressure buildup. We call that P naught. That's proportional to the temperature rise, which is in turn proportional to the absorption coefficient times the optical fluence. So even though we're measuring a quantity related to P naught, which is a mechanical quantity, indirectly we're measuring optical contrast given by the absorption coefficient mu A. You can solve the differential equation, come to this integration. So P naught is the initial pressure buildup. It's a function of space. This delta function will give you this definition, which will select a spherical shell out of 3D space. So essentially, we're integrating the initial pressure buildup over a spherical surface. That's called spherical radon transform, very much analogous to the linear radon transform used in X-ray CT or positron emission tomography. So you can solve this fairly easily if you know the material properties. You can predict what kind of pressure you should observe if you know the object. That's the forward problem. Let's give you a very simple example. Let's assume there's a spherical object, uniformly absorbing light. Right after the laser pulse, you would observe a pressure like this outside object. If we place an ultrasound detector right here, this bipolar profile is what you should expect. So this is time. Well, to think about this, you can divide this solid sphere into many, many layers, concentric spherical shells. The outermost shell is going to give you two pressure waves. When you build up the initial pressure P naught, it's going to counter-propagate in two opposite directions. The outgoing diverging wave is the leading edge of this wavefront. And the converging wave will go toward the center, but once it reaches the center, it's going to be quote-unquote reflected through the center, and the positive pressure will become negative. And then becomes divergent again, and that becomes this trailing wavefront. So that's going to end up giving you a circle here in this simulation. That's the last circle, the most negative value. All right, now you can compare, figure out the next layer. It's going to give you a pair of circles as well, and that's the next pair from the second highest, most positive value, from the second most negative value, and so on and so forth. You can just go stepwise toward the center. Right? If you know how to do this, you can apply the same equation for an arbitrarily complex object. So that's the forward problem. Now, of course, for imaging, we got to solve the inverse problem. Let me talk about photoacoustic CT in the circular geometry first. You start from an unknown object, so we don't know the pressure distribution to begin with. You expand the laser beam, make sure you're safe. There's an NC safety limit. Now, the difference between this modality and all the standard ballistic imaging modality is we allow photons to scatter and still remain useful. In ballistic imaging, you try to retain the ballistic photons and reject all the scattered photons. As a result, you won't penetrate deep. Here, any photons are good photons, scattered or not. As long as photons are absorbed, it generates heating. As a result, it's going to generate ultrasound emission. Every millidegree temperature rise will give you 800 pascals pressure rise. All we have to do is to detect the ultrasound emission outside the tissue. From there on, it's a mathematical problem to form an image. Let's start with the simplest analogy. If you have a point target, let's say there's a thunderbolt. How do we pinpoint that thunderbolt? When you see lightning, you reset your stopwatch. That's your time 0. When you hear the thunder, you record a time delay t1. Multiply that time delay by the speed of sound, you get a radius for a spherical shell on which lightning took place. If we have 3 such measurements centered at different locations, the intersection of the 3 spherical shells will pinpoint the thunderbolt. So this is the basic principle behind photoacoustic CT. Extremely straightforward. Except in reality, we don't have a point target. We have a complex 3D target. So the math is a little more sophisticated. Here again, a 3D complex object, which is unknown to begin with. We can base this object with photons by expanding the laser beam, fire the nanosecond laser pulse onto the tissue. Right after time delay t1, you form this spherical radon transform, so the detector reports a single number that stands for the radon transform integrated on this spherical shell. Now, of course, the speed of sound is so slow, so we have very good temporal resolution. This detector is going to report a time trace. This is very different from X-ray CT because the speed of light is so high, we don't really give you time resolution in X-ray CT. This time gives you the extra dimension for photoacoustic computed tomography. The best they can do is to place a lot of detectors on a detection surface. Radon never really inverted this problem, so we had to work on this problem. A number of mathematicians are very interested in this problem and provided solutions. And our group was interested in this as well. In the early days, we had one solution for each geometry: planar, cylindrical, and spherical. Very likely, we found a universal back projection algorithm that works for all 3 detection geometries. It turned out to be also very simple. P is what we detect on the detection surface or not as a function of time t. We have to properly time delay the signal for reconstruction, because when the signal was received, there was time delay. When you reconstruct, you got to properly put the signal back through the right time delay. And we use the solid angle to integrate the different geometries. If you were to use the pressure only, you get an approximate solution to the initial pressure buildup P naught. This is very similar to ultrasound beamforming. Now, if you were to include this temporal derivative, which is essentially the high frequency component, you get an exact solution of P naught. So mathematically speaking, that was very exciting. In 2003, this was the first functional photoacoustic tomography. We demonstrated this concept in a small animal. By wiggling the whiskers of the small animal, the contralateral side of the brain was activated. And we see the hemodynamic change of the brain in response to the whisker stimulation, depending on which side you wiggle the whiskers. So this set of images were acquired totally non-invasively. We depilate the head, but the skin and skull were intact. So light had to wander through the skin and skull, reach the brain cortex to excite the blood vessels in order to emit photoacoustic waves. This work was exciting enough at the time to galvanize the field. As you can tell, since 2003, this field has grown exponentially with a doubling constant of roughly 3 years. I'm plotting the number of papers presented in the Conference on Photons plus Ultrasound, which is the largest conference on this topic. This conference was part of Photonics West, which is the largest gathering in biomedical optics. So since 2009, this conference became the largest in Photonics West. And it's growing even further, so now it's the largest by far in that conference. A very natural question is, why is photoacoustic tomography so exciting? Why are there so many people jumping into this field? In my opinion, Every imaging modality has strengths and weaknesses. But photoacoustic tomography is the only one that allows you to provide multi-scale imaging in vivo using the same contrast mechanism, optical absorption. Because that's what we detect. Well, why is that important? In current practice, for organelles and cells, we use optical microscopy. So we're imaging optical contrast. For tissues and organs, we use MRI, PET, ultrasound, whatnot. Non-optics. So we're looking at non-optical contrast. There's a huge divide between the microscopic and the macroscopic worlds because we're looking at different contrast mechanisms, which makes it really hard to correlate images acquired from different length scales. Why is that important? My hope is that photoacoustic tomography will enable systems biology research at multiple length scales, which is believed to be the future of biology. Practically speaking, photoacoustic tomography can potentially accelerate translation of microscopic lab discoveries to macroscopic clinical practice. We don't translate enough new discoveries. We have tons of exciting new discoveries in the lab on the microscopic scale, but very few of them are translated successfully. Because part of the reason is this huge divide between the micro and the macro domain. Each bar here represents a system constructed by our lab. And so we're plotting the penetration capability over the resolution. Okay, I'll come back to this map repetitively as we introduce each system. For this first photoacoustic image acquired over a small animal brain for functional imaging, we used a single element transducer rotated around this small animal, and we fired a laser pulse at every position of the transducer just to mimic an ultrasound array, right? Because that was the only system we had at the time. An ultrasound array would be much more expensive. So the initial data acquisition took about 20 minutes just to scan around. In collaboration with a group at UConn, led by Professor Zhu, now we have an ultrasound array made of 512 elements. Using parallel detection, within a couple of seconds, we can acquire the entire data set for a 2D image. So we apply this system for full body small animal imaging. Would you dim the light? Thank you. So we're scanning the system along the animal trunk, up and down. We're looking at different cross sections of this small animal. And so the organs will become in focus and out of focus. What you do is, this is a still image, one of the shots in the movie. For example, you look at the colon, and you'll see the colon will be out of focus to begin with, then it'll become in focus, then it'll gradually become out of focus again. You can repeat it for any of the other organs. So this becomes very exciting because for pharmaceutical studies, we want to observe the animal without using ionizing radiation, using intrinsic contrast only. So we're imaging hemoglobin blood as our endogenous contrast. Let me talk about photoacoustic CT in linear geometry. In collaboration with Philips, we've adapted a clinical ultrasound machine for concurrent photoacoustic tomography while we retain the original imaging capability by using ultrasound. This is a ultrasound linear array with 256 elements. We flanked the ultrasound probe with 2 fiber bundles for light delivery. You fire a single laser pulse, light will be delivered into biological tissue. All 256 channels of ultrasound array will receive the signal in parallel. And it allows you to form a 2D image. So every laser shot gives you a 2D image. Intrinsically, this is an extremely fast data acquisition system. And this is another configuration showing you how light is delivered into tissue and how the probe receives the photoacoustic signal. We're targeting a number of applications using this system because the system can penetrate a few centimeters into biological tissue and still provide you about a millimeter in resolution. One of the applications is reporter gene imaging. As we know, Roger Chin et al. Received a Nobel Prize 3 years ago for their work in reporter genes, which was based on fluorescence imaging. If you were to use pure optical imaging, you face the same issue as we discussed. So you have high resolution at a very shallow depth, then you lose the resolution very quickly. Using photoacoustics, we can image reporter gene expression products at a depth of 5 centimeters and still give you about a millimeter resolution, which was not possible by using fluorescence imaging. One of the first questions for optical imaging is how deep can you penetrate? Because our intuition is that light will not penetrate in tissue. That's not true. Light will not penetrate in tissue in a straight fashion, but if you allow photons to scatter, they can penetrate. So this experiment shows that in an ex vivo experiment that we can penetrate about 7 centimeters and still give you about a millimeter resolution in biological tissue. But this was ex vivo. Eventually, we got to move into in vivo experiment. So recently, we started human imaging using this system. This is the very first patient we imaged using this handheld probe. And you can see even at a depth of 6 centimeters, there are still features you can observe. So I was very excited to see this first image. Whatever you do ex vivo is approximate solution, right? You got to do it in vivo in real patients. So that demonstrates the penetration capability of our imaging system, multiple centimeters. The real experiment we're interested in is to stage the breast cancer. Right? In the US, at least when a cancer patient, breast cancer patient, is confirmed with breast cancer, we have to stage the patient for stage 1 through stage 4. The idea is that if there's any metastasis, they have to go through the first draining lymph node or the sentinel lymph node. In current practice, we inject radionuclide, we inject optical dye like methylene blue dye. Both will flow toward the sentinel lymph node. Then we use a gamma photon receiver to roughly locate the sentinel lymph node. We cannot pinpoint it. The physician then cut open the breast, in the OR, of course, then visually follow the dye, the optical dye, until we pinpoint the sentinel lymph node invasively. Then dissect the sentinel lymph node, do histology. If there's any metastasis, that's cancerous. If it's non-cancerous, the patient is fine. 80% of the patients who go through this procedure turned out to be benign. In the US alone, every year we conduct 100,000 cases of surgery. So 80%, 80,000 of them are unnecessary surgeries. We want to convert that open surgical procedure into a needle biopsy procedure. The first requirement is to pinpoint the sentinel lymph node. Using our technology, once you inject the methylene blue dye, which is FDA approved, we can see this spot light up with a very high contrast. In this case, the contrast is at least 6:1. So our next goal is to insert a needle, use the same technology to guide the needle toward the sentinel lymph node. Then take the tissue out for cytology or histology. Now, photoacoustic tomography also works in microscopy. Let me first talk about the acoustic resolution version. In photoacoustic CT, we use unfocused ultrasound transducer. We depend on math to form an image. In photoacoustic microscopy here, we depend on physics to form an image. Let's assume there's an optically absorbing target in a scattering tissue. We fire a laser pulse, generate photoacoustic wave, then use this focused ultrasound transducer to receive the photoacoustic wave. And you get this time trace. this target becomes a spike right here. Well, you can imagine if you have a second target somewhere deeper, you would have a later arriving spike. We do Hilbert transformation of this time trace to form an envelope for envelope detection, and that will give you a one-dimensional image called a scan. It's a depth resolved image because we can convert time into depth as we know the speed of sound very well in soft tissue. If you scan across this tissue, you form a two-dimensional B-scan image. If you raster scan on the surface, you get a 3D image. This is the first 3D photoacoustic microscope. Starting from a laser, route the laser beam through optical fiber. The solid beam comes out of the fiber. We convert this solid beam into a hollow beam through this conical lens. This hollow beam is refocused down through this element, shown in this close-up, onto the tissue. On the tissue surface, we have this donut beam. So the core is dark just to minimize the surface interference. This ultrasound transducer is confocal with our light illumination just to maximize the signal-to-noise ratio. This scanning head is raster scanned in this water tray. Through the membrane window, we transport light and sound. So the tissue we want to image is placed below the membrane window. This system works around this spot. A few millimeters penetration, tens of microns in resolution. This is a photograph of a melanoma, which is the most deadly form of skin cancer. Well, while we can see a little bump, but we can't tell the depth of the melanoma, we cannot see the surrounding blood vessels. Most melanomas have increased melanin concentration. So by detecting the melanin, which is a great absorber for light, we can see the melanoma extremely well. Then we use hemoglobin as endogenous contrast to see the blood vessels. So we're using two different laser wavelengths to see both tissue components, two types of absorbers. And you can see how high the endogenous contrasts are in this type of images. I mean, if you were to use X-ray to image soft tissue, you're talking about typically 1% contrast. Day and night differences. And we're trying to apply this technology to the dermatology clinic by working with our dermatology chief, Dr. Cornelius. We can image humans using this system. Again, using endogenous hemoglobin as our contrast, you can see the blood vessel network very well. And you can see all these depth resolved images showing the standard skin structures. Photoacoustics is very compatible with nanotechnology. Many nanoparticles are highly optically absorbing. They can provide you very high optical contrast. This is an example by using nano cages. They're gold nano cages. And there are two types of nano cages here. One is simply plain nano cages. The other one is targeted nano cages. So this targeted version of nano cages are smart enough to target MSH receptors. These are melanocyte stimulating hormone receptors, which are hallmarks of melanoma. The targeted version is going to give you a contrast enhancement by 3-fold in comparison to the non-targeted version. And what's useful here is the nano cages are capable of controlled drug release. Because these nano cages are hollow, you can load the nano cages with drug and then wrap the nano cages with polymer, and the polymer is temperature sensitive. If you heat up the nano cages, the polymers will shrink, open up the pores at the corners of the nano cages, then you can release the drug. If you cool down the nano cages, the polymers will wrap the nano cages again, and you can come back for repetitive treatment. And we can use photoacoustic tomography to monitor the entire process. Endoscopy is another target for us. In standard optical endoscopy, you have a penetration of roughly up to 1 millimeter. But physicians want to penetrate 3 millimeters or more. Using photoacoustic endoscopy, we can penetrate up to about 7 millimeters. Well, the key in this device is this rotating mirror. We transport light through this optical fiber. Light is reflected by this mirror onto the tissue you want to image. And photoacoustic wave comes back, reflected by this mirror surface, received by this ultrasound transducer. So ultrasound transmission does not like air. This chamber, as a result, is liquid filled. The micromotor does not like liquid, so this side of the chamber is hermetic. We separate the two chambers, but transfer the torque through a pair of magnets. And you can see this device in action, and these are in vivo images acquired in vivo from this rabbit esophagus. So we're pulling back. You can see the blood vessel structures very well in the photoacoustic image. At the same time, we acquire ultrasound images. These are 3D rendering of the two types of structures. And so we're working with our GI specialist trying to apply this in vivo in humans. A related application is colonoscopy, or for colon cancer screening. But the first targeted application is for Barrett's esophagus. So this acoustic version penetrates a few millimeters, but we're also interested in top 1 millimeter. We're back within optical diffusion limit. Within the optical diffusion limit, light can still be focused. There's enough photons for you to use for optical focusing, ballistic photons. So here, light is focused into tissue. You generate a photoacoustic pulse, then you receive it using ultrasound transducer. The key component in this device is this light-sound combiner. How do you align your optical and acoustic axes in this setup? In this combiner, we use two prisms with a gap in between. The gap is filled with liquid. Along the optical axis, the optical refractive indices are highly matched, giving you very high light transmission. At the interface, the acoustic impedances are highly mismatched because one side is solid, the other side is liquid. As a result, ultrasound is highly reflected. And so we can use this ultrasound detector to receive the photoacoustic wave. With each laser pulse, we get a 1D image, depth resolved image, very much like this acoustic resolved version. So then you can raster scan to form a 3D image. In this case, your transverse resolution is defined by the excitation, right? By how well you focus your optical beam. But your axial resolution comes from the time of arrival of the acoustic wave. So that depends on your bandwidth of your ultrasound detector. This device works in this regime. It penetrates about 1 millimeter in scattering tissue with a resolution of a few microns that can be even improved for submicrons. One of the first applications is to monitor angiogenesis. We work with our biologist who used to sacrifice animals at different time points to build a database like this. He had a headache with intersubject variability, right? Because every animal is different. Here we monitor the same animal over a period of 60 days. And you can see increase in vessel density, increase in vessel tortuosity. And in the old fashion, you had to sacrifice a lot of animals to get a data set like this. Here we monitor the same animal. We don't have to deal with intersubject variability at all. And this is a 3D rendering of the data set. That first device was a 5-micron resolution version. We improved the resolution to 2.6 microns. You can image the entire ear of a small animal using intrinsic contrast only. Right. This image is so dense, you have to zoom into a small area that allows you to see capillary beds, single capillaries. All these single dots are single red blood cells. So we have single cell resolution, single cell sensitivity, using intrinsic contrast only. If you were to use micro CT, micro X-ray CT, you have to inject contrast agents. Even with exogenous contrast agents, you still miss capillaries because there's not enough contrast for you to image with. This is a 3D rendering. Now, better yet, because there are two forms of hemoglobin, oxy and deoxy hemoglobins. They have different colors. Their absorption spectra are different. If we tune our laser wavelength, we can measure the concentrations of both forms of hemoglobin, from which we can compute a very important physiological parameter called oxygen saturation of hemoglobin, or SO2. So here we're plotting SO2 in pseudocolor. Red means high SO2. They are arteries. And blue or green have lower SO2 because they're veins. So that's known in physiology. So here we're essentially doing single vessel oximetry. You've heard of pulse oximetry. That's volume averaged with no single vessel resolution. And also pulse oximetry measures arterial vessels only. They cannot image veins. Here we can image both arteries and veins. Better yet, recently we demonstrated we can image a single cell. We can do not only single vessel oximetry, but single cell oximetry. Here we're following red blood cells as they flow through a single capillary and monitor its oxygenation status. So this pseudocolor bar is for SO2. You can see as cells flows through, and they'll change their color because cells will unload oxygen as they travel in the capillary, and as a result their color will change. And so now we're doing single cell monitoring and monitoring single cell oxygen metabolism. That's extremely important in physiology. This is what you see for animal head after the hair is depilated. You can't really see through the skin and the skull and see any of the structures in the brain cortex. There's enough scattering to mess up the image. But using our device, photoacoustics, you can see the internal structures of the brain cortex. And this is endogenous contrast only. Well, if you remove the scalp, so you can see through the skull some of the structures, you can compare and see how well we can image non-invasively. At this stage, if you use a higher resolution photoacoustic microscope, you can get a detailed map of all the capillaries. So this is extremely useful in neurological studies. For human imaging, we image our own fingers. You can see all these capillary loops. These are the smallest blood vessels in our fingers. We can also monitor the oxygen saturation. You can zoom into a single capillary loop. You can see one side of the loop is highly oxygenated because it's shown in red, and the other side is shown in green, which means the sharpest gradient is at the tip, which means most of the oxygen is unloaded at the tip. This is an entirely new phenomenon in physiology. Not only can we image the total concentration of hemoglobin, the oxygen saturation of hemoglobin, but also the velocity by using the photoacoustic Doppler effect. This is a new physical phenomenon that was observed by our lab a few years ago. And you've heard of ultrasound Doppler, you've heard of optical Doppler, but there's also photoacoustic Doppler. Why is that important? With all these three parameters in combination with the images of the blood vessel cross sections in the region of interest, we can quantify a very important physiological parameter called the metabolic rate of oxygen. Well, why is that so important? Look at cancer. Cancer has a problem with metabolism. Cancer, by definition, is hypermetabolic. We studied glioblastoma, which is the most deadly form of brain tumor, in a small animal. So on day 7, we see this increased MRO2, the metabolic rate of oxygen, showing the hypermetabolism of cancer. But very surprisingly, we show this hyperoxia instead of hypoxia, because we commonly believe tumors are hypoxic, but in the early stage that's not very true. So by definition, if we were to use the metabolic rate, we might be able to provide the earliest form of cancer detection. And we're using intrinsic contrast only because for screening purposes, you don't want to inject contrast agents. Here we're using intrinsic contrast only. As we know, every physician has two eyes, radiology and histology or pathology. But in the standard practice now, histology by definition is invasive. You have to cut the tissue open, then prepare the tissue, then look at it under a microscope. For surgery, if you want to clear the tissue, clear the tumor margin, you sometimes have to go back and forth between the OR and the histology department. We want to provide in vivo label-free histology by using DNA absorption and RNA absorption. So this is what we can see. We see a distribution of cell nuclei non-invasively and label-free. And this is what you see using standard histology, but you have to label. You do HE staining. And you see cell nuclei distribution as well. You can see how well they correlate. So if we can provide you label-free in vivo histology to work with surgeons in the OR, we can do everything in one go and just clear the tumor margin. What is the best resolution we can provide? So we try to push the numerical aperture, try to focus light as tight as possible. And we achieved 220 nanometer resolution as shown in this image of a single nanoparticle. This device works in this region. Well, I need to wrap up. When things start working, we tend to forget about all the difficulties, and we take everything for granted. And there are probably many, many ways of combining two forms of energy. There are even more ways of combining maybe three forms of energy. So here we're combining ultrasound and light. But not all combinations work equally well. One of the key requirements is signal-to-noise ratio. So in theory, there's no difference between theory and practice, but in practice there is. So we have really to look at the signal-to-noise ratio, because if the SNR doesn't help you, your technology will not work. Look at photoacoustics. This conversion ratio, without going through the details, depends on beta, the volume expansion coefficient, and kappa, the compressibility. And that ratio turned out to be 8 millibars per millidegree. A good transducer, ultrasound transducer, has the sensitivity at millibars. So that means we have the sensitivity of millidegrees. If you generate hundreds of millidegrees, then you have a good SNR to work with. So every time I look at this constant, we don't control this constant. The material properties determine this constant. If this constant is less efficient, we have to cook tissue to generate enough SNR. In reality, we don't have to do that right now. So I really appreciate this constant. Another constant, another conversion. Look at the penetration versus axial resolution in this modality. The resolution in both the lateral and axial direction is inversely proportional to the ultrasound frequency, but ultrasound attenuation is proportional to the frequency, so the penetration is inversely proportional to the frequency. But the ratio is relatively independent of the ultrasound frequency, and we don't really control that ratio very well. That's all material property dependent. And it turned out that constant is 200. That means we can provide you 200 pixels to work with. If that constant is 2 instead, we'll only give you 2 pixels. You'll hate our images. So now we have high resolution images because of this constant. We all need nature's help. If you were to switch the laser out and use a microwave generator instead, you can penetrate even deeper. I'll not get into the details. So this is a microwave-induced photoacoustic tomography instead of light-induced. Just bring this new concept to your attention. We said diffuse light is really hard to focus, which is still true. But recently we found out if you generate a guide star, a virtual guide star in biological tissue, you can do time reversal. Very much like astronomers doing time reversal by using a guide star. So they want to correct the aberration due to the atmosphere. In our case, we use a focused ultrasound to generate a virtual guide star, and that modulates light outside the tissue. We detect the ultrasound modulated light and then use a phase conjugation mirror to time reverse it back into the ultrasound focus. So if this works eventually in biological tissue in vivo, it can impact imaging, sensing, manipulation, and therapy. Everything you want to do with light can be potentially impacted by this technology. In summary, photoacoustic tomography is achieved through optical excitation and ultrasonic detection. The diffusion limit has been broken. Super depths up to 7 centimeters have been reached. Single capillary cells, even organelles, can be resolved in vivo. Multi-scale imaging is achieved by scaling the depth and resolution. We have background-free detection, which is built-in photoacoustics. So that means the sensitivity to optic absorption is the highest among all modalities. Either non-fluorescent or fluorescent pigments can be imaged. Basically, you can say any molecules are absorbing. It's a matter of finding the right absorption peak. Multiple chromophores can be resolved spectrally. Functional imaging comes from endogenous contrast. Molecular imaging comes from targeted contrast. Reporter genes can be imaged, so we can follow gene expressions. Doppler imaging comes from the photoacoustic Doppler effect. We can use that to image blood flow. Data acquisition is extremely fast. It's limited by the ultrasound propagation through the region of interest. There are no spectral artifacts, very different from ultrasound images or OCT images. We only use non-laser radiation. The systems are relatively low cost. However, I have to mention that we do require contact detection by using gels or liquid. If there are air cavities, the ultrasound transmission can be very challenging. And very thick bones can present challenges as well. So here's the book. If you're interested, there's a chapter on photoacoustic tomography written in a tutorial style. The book is entitled Biometric Optics, Principles and Imaging. And there's also an edited book. Most of our experts in working in this field have contributed to this book. Thank you very much.
We'll take very brief questions. The idea of this afternoon is to have you pent up your questions to the panel discussion at 5 o'clock. But if you just can't stand not asking a question right now, go ahead. Yes?
How does this modality perform against any other modalities like MRI in terms of sensitivity, let's say in breast cancer?
So we haven't done breast cancer imaging yet. So we haven't really compared head to head, but they work very differently. So MRI measures nuclear spin, so we measure electronic transitions. So we image molecules directly instead of nuclei, atomic nuclei. So the contrast mechanisms are extremely different. So we're very sensitive in terms of molecular imaging. We're very sensitive in terms of functional imaging. For example, we can see both forms of hemoglobin, oxy and deoxyhemoglobin. MRI is primarily sensitive to deoxyhemoglobin. So there's ambiguity when they try to quantify oxygen saturation and total blood volume. And there are many, many differences. Most likely we'll be more sensitive than MRI, but MRI will have probably more penetration than our technology. So eventually everything will be complementary.
Very quick
question. Have you tried this in pulmonary embolus?
In
Pulmonary embolus.
We haven't tried that particular problem. How deep are we talking about for that?
Pulmonary vasculature, so kind of around the great vessels of the heart.
Yeah. No, we haven't tried that, but we're actually writing a protocol for heart imaging. So we're moving in that direction.
Right, we'll save all our questions for 5 o'clock, and now it's up to Dr. Robert Lees from Oxford to introduce the remaining speakers.
Thank you, Adrian.